Okay, we'll move on to the next one. Dan Moriarty and co-authors, Ancient Lunar Mantle Ejecta Preserved on the Lunar Farside. Dan, are you ready? You have
I
5 minutes.
Thank you very much. Carla, you'll have to tell me where to get one of those Spinel shirts. Those are pretty great. Okay, so in this talk, I'll be discussing what we think is one of the most compelling targets for lunar sample return. And that's Ejecta from the South Pole Aitken Basin that provides a snapshot of the ancient lunar mantle. Next slide, please. That's Carla. Yep, perfect. Currently, there are no confirmed mantle materials in the lunar sample collection. So acquiring samples of the lunar mantle is a high priority target relevant to several fundamental planetary science goals, including understanding primary differentiation, as well as thermal evolution processes. So what does the upper mantle look like, and where should we go to get some? These questions are not as straightforward as they might seem, and there's actually a good amount of disagreement within the lunar science community. So we addressed these questions in a pair of recent papers in Nature Communications and JGR Planets, which are shown here. And I'll sprint through the essential takeaways of these papers over the next few minutes. So lunar differentiation is understood to have occurred through solidification of a deep global magma ocean. One of the primary focuses of our papers was tracking the fate of late-stage lunar magma ocean cumulates, which are enriched in incompatible elements, including titanium, thorium, iron, and rare earth elements. So in other words, ilmenite and creep. Next slide, please. Based on petrological models, this late-stage assemblage is understood to be mineralogically distinct from earlier, deeper mafic mantle cumulates. It's enriched in clinopyroxenes and oxides such as ilmenite. It's also relatively dense and probably plays a big role in the gravitational restructuring of the lunar interior. This assemblage is also enriched in heat-producing elements, and its fate may affect the thermal evolution of the moon. Next slide. Next slide, please. Yep. So in the papers, we integrate remote sensing data with numerical models and laboratory experiments to identify and characterize candidate mantle materials exposed on the lunar surface. On the right, we're showing the results of a three-dimensional impact model of mantle-derived ejecta from the South Pole Aitken Basin, convolved with subsequent geologic evolution through impact and impact crater and basin formation. So the resulting pattern in the ejecta blanket is remarkably similar to the distribution of thorium observed by Lunar Prospector. Since we know that thorium should be enriched in the late-stage lunar magma ocean cumulates, this suggests that SPA did indeed excavate this kind of late-stage mantle assemblage. Next slide, please. Next slide, that's the previous slide. Perfect. So our hypothesis is supported through further analyses of other remote sensing products, such as Lunar Prospector potassium abundance on the right, as well as some of the geologic associations we observe. So for example, later large basins such as Apollo appear to have completely excavated through the SPA ejecta blanket, locally removing the thorium signature. Whereas volcanically resurfaced areas also exhibit local minima in thorium abundance, showing kind of resurfacing, the effect of resurfacing. Whereas recent medium-sized craters, 50 to about 100 kilometers, appear to be re-excavating the thorium-bearing materials from beneath a mixed diluted regolith superficial layer. Next slide, please.
One minute, Dan.
Yeah, if it could be the next slide, not the previous slide.
Keeps going back and forward.
I know. I have no idea why it's doing this. I'm literally doing the same exact thing.
Yeah.
I am trying desperately to move forward, and it's going backwards.
Anyway,
Okay.
I'll just keep
I'm going to
speaking while we
escape
try
and
to
then
grab the
load it
slide.
again. Give me 1 second.
Okay.
And
So we also see
slide.
that titanium and iron are correlated with thorium. And in moon mineralogy mapper data, these materials are found to exhibit the clinopyroxene-rich mineralogies that we'd expect as predicted by lunar magma ocean crystallization models. So what that means is that we can use M-cube data for a much higher resolution look at the distribution of these mantle materials than you'd be able to get from a coarse resolution instrument like Lunar Prospector. So if the slide were being presented, we'd be showing M-cubed maps of Birkeland and Oresme V, which offer the most pristine exposures of this mantle material currently available on the moon. Okay, and yeah, we can leave this slide right up for the final bit. So essentially, the thorium-bearing materials we observe across SPA we find to be the remnants of late-stage lunar magma ocean differentiation. So the two thorium hotspots, Birkeland and Oresme V, they're the highest thorium abundances in the region. And we interpret these to be the freshest, most pristine, large-scale surface exposures of mantle material currently identified on the moon. And so these materials as candidate sample return sites are relevant to numerous high-priority science questions related to planetary differentiation, thermal evolution, and the nature of the lunar dichotomy. For this very high value, but also very complex target, we recommend sample return as the most appropriate approach for addressing these science questions. Thank you very much.
Brilliant. Thank you, Dan.